Okay, so I've posted some extra problems for test 3, which is Thursday, right? So let's just write this up. So extra problems on Leia. That's done. Test 3 is Thursday. It covers chapters 9 and 10, right? Yes. So I'm gonna do some problems from chapter 10. I've done some from chapter 9 already. So let's there's something I might not have done enough of, which are about sigma notation. In the WebWorks, some of the hardest problems were on sigma notation. I didn't spend that much time on it because it's sort of a minor topic in what we're doing. And so I wouldn't worry about those too much. Okay, so some of the problems were harder in the WebWorks, but that was just for to challenge you a little bit. But don't expect things to be too hard as far as sigma notation goes. Okay. So now I'm going to do some problems from the book. Let's take a look at this. So so this is on page 255 in the book. So let's start with a couple of back substitutions. So this is number 23, A. So we're asked to solve the following system: x plus y minus 3z equals to 5, 2y plus z equals to 8, and 3z equals to 6. Okay, so I'm just gonna copy this up and switch pages. Okay, so you can probably see, yeah. And Hisham, your question is, you want me to do one like that?
Yeah, please, if you can, because I
Sure.
didn't understand it.
Okay.
Thank you very much.
Okay. Yeah, okay. I don't know if I guess I'll have to go to chapter 9 for that. But anyway, let me do some back substitution first, and then I'll get to that problem. Okay, so as you can see, this is a upper triangular system, or if you want, the matrix of coefficients is upper triangular. So it's basically just back substitution. There's no elimination needed. It's already solved in a sense. Okay, so again, how does this work? You start at the bottom, right? So we've got 3z equals to 6. This, of course, gives you that z is equal to 2. Okay, once you have z equals to 2, you go to this. So this is, let's number these. This would be equation 3, equation 2, equation 1. So I start with 3, then I go to 2. I've got 2y plus z equals to 6. But now I know that z is equal to 2. So this gives me 2y plus 2 equals to 6. And so 2y equals to 4 and y equals to 2, right? And finally, once I've got these two out, yes?
In the book, I think it says that 2y plus z equals 8.
Yeah.
At least in my book.
Oh, yeah. Okay, so I wrote 6 here. Sorry, thanks. Yes. Let's change that.
I think someone's in the waiting room.
Yeah. Thanks. 2y plus z is equal to 8. Z is equal to 2, so 2y plus 2 equals to 8. So 2y equals to 6. So y equals to 3. Yes. All right. Thanks for spotting that. Okay, so then once I've got these two, I go to the next equation, which is x plus y minus 3z equals to 5. I also have now that y equals to 3. So this is x plus 3 minus 3 times 2. I found z equals to 2. This is 5, right? So this goes here. Get that. And so x plus 3 minus 6 equals to 5. And so x equals to 5 minus 3 plus 6, which is 8. So x is equal to 8. And so we've solved it. So solution is unique. It is x equals to 8, y equals to 3, z equals to 2. What you should do once, let's say that you have some extra time, which hopefully you will have. You reach your unique solution like that. What you can do now is, of course, substitute back in all three equations to make sure that it works. Of course, if it's just a back substitution, I mean, you're not going to learn much from this because you'll be just unraveling what you just did. But if you have a full system that you have on which you have to do Gaussian elimination, then if you have your solution at the end, you go back to the original system, two things can happen. Either it doesn't work and then you know you have to do it correctly again, or it works and you're super happy because you know you've got it right. So that's a very good
Sir,
reason. Yep.
in a web work, I had the answers were right. However, when they asked me to write the solution in the X, Y, Z, T, I wrote it as follows inside the parentheses. I wrote X equals the answer, Y equals the answer, all the way to T. But then it says unexpected character, which is the equality sign.
Yeah. So they
So I don't
wanted,
understand why
I guess
what
I'd
I
have to
did.
go and look at the way the question is phrased, but they probably wanted it as a vector, right? So something like x, y, z equals to 8, 3, 2, right? That's another way of writing it. It means the same thing. So of course, WebWorks expects it in some specific form. So that could have been it, but I don't. You'd have to show me the question.
Oh, okay.
Yeah.
I'll look
So,
it up. Okay, thank
yeah.
you.
Okay, so that's a back substitution. Okay, let me try to fish out a problem like in the WebWorks. I think I saw one like that. Let's see. Or maybe I'll just pick one out from the WebWorks. That's the best. Okay, I'll just go and. So here's one from the WebWorks. Let's see. This. This. Okay. Let's see. okay, like this one. Find values of S and T such that we're given the following vectors: 6t plus 1, 2s minus t equals 4s plus 2t, 3 minus 5t.
We can't see what you're drawing currently.
Yeah, nothing shows up.
Okay. How about now?
Yes.
All right. Thanks. Okay, so point number one is that you have to remember that for matrices and vectors, it's always the same. So if you have equality between two matrices or two vectors, what it means is that you have equality for each corresponding component or entry. Okay, so this means that 6t plus 1 is equal to 4s plus 2t, and 2s minus t equals to 3 minus 5t. Right? So two vectors are equal means that their corresponding components are equal. That's what it means. Okay? So if you look at this, you have to take a step back, okay, and take a look at what you have. You have two equations. There are two unknowns, S and T, and then you look at the shape of these equations and they are linear. So it's a system of linear equations. Now, again, in theory, for two variables or two unknowns, two equations, you've seen how to do that in high school, but you can still use the techniques we have seen now to solve the system. It's either way, right? So what you need to do here is to solve this system. I'll just rewrite it. 6t plus 1 equals 4s plus 2t. 2s minus t equals 3 minus 5t. So certainly what I'm going to do is to rewrite each equation in the standard form, right? So first one, I'm going to get 6t minus 2t minus 4s equals to minus 1. Okay, so I'm putting all my variables on the left-hand side and the constants on the right. I'll do the same for the second one. I've got 2s minus t plus 5t equals to 3. Okay, and then I'm going to put all the variables together, right? So 6t minus 2t, I'll put s and then t, why not? Minus 4s plus 6t minus 2t, this is 4t, equals to minus 1. 2s, and that's 4t equals to 3. Okay, so you see that you have a system of linear equations with two unknowns, two equations, two unknowns. Okay, so you can do it. There are many ways you can do this. You can do this with Gaussian elimination. Okay, let's just copy this and go to the next page. Let's go here. Okay, so to solve this, you can do it by Gaussian elimination. That'll work. It always works. Or from high school, you can just do substitution, elimination and substitution, which is just basically the same thing, but okay. So for example, here what I could do is just do first equation or second equation minus the first, right? So I could do second equation minus the first equation. Why am I doing that? Because I see that I have 4t in both, so I'll get rid of the t, right? So if I do left-hand side, I'm going to get 2s minus 4s plus 4t minus 4t equals to 3 minus 1, right? So this will give me 6s equals to 4, right? And so s equals 2/3. Okay? Once I have s equals to 2/3, I can substitute in either one. Right? I'm doing it high school style. Okay, so s equals to 2/3. So I'm going to get 2 times 2/3. I'm using the second equation here, plus 4t equals to 3. So this gives me 4/3 plus 4t equals to 3. And then solve for t. So 4 plus 12t equals to 9. And so 12t equals to 5. So t equals to, I'm doing it fast. I might be making some mistakes here. I think it's okay, but okay. So, but you can do Gaussian elimination also if you prefer. Okay, I don't want to do it with Gaussian elimination here. I want to do a bigger one, which was my plan all along.
So in this case, what's the resulting vector?
S equals 2/3 and t equals 5/12. That's what I get. These are the values I'm asked for. So that's what I get in that particular example. Is that your question? Sorry.
I mean, in the web work, not only it asks for the value, but also it asks what's the resulting vector.
Ah, okay. Yep. So I have to go back to this. So you look at this and you just plug in the values you found for S and T, right? That should give you the same thing on both sides. So let's copy this. Okay, so we found S equals to 2/3, T equals 5/12. Hopefully I didn't make a mistake. So then you just plug in those values. So you'll get 30 over 12 plus 1. And 2s, that's 4/3 minus 5/12. That would be the vector. Just, you can simplify if you like, but hopefully gives the same thing on both sides. Again, I might have made a mistake.
Okay, thank you, sir.
All right. Okay, all right. So I'm going to go back to chapter 10. This is number 25A. Okay, so we're asked to solve the following system: x plus 2y minus z equals to 3, 2x plus 5y minus 4z equals to 5, and 3x plus 4y plus 2z equals to 12. Okay, so I'm asked to solve the system. You see linear equations, 3 unknowns, 3 equations. Okay, so what I'm going to do, I'm going so basically what I'm going to do is just to review everything we saw in chapter 10 in a sense, just the whole method, the matrix representation, and so on and so forth. Okay. So there's, yes, there is one thing that I'd really like you to do on the test, because you can probably guess that you're going to get something like this, right? And is to indicate which elementary row operations you are doing, because, and I'm going to explain this in a sec when I get there, but if you don't tell me what you're doing and you mess up, then it becomes extremely painful to try to figure out what you did, right? Because all we see is just a bunch of numbers, and if you make a mistake, then nothing works. I mean, we can just try to figure out, so that was row 2 minus row 1 or what, I don't know, is just it's a huge mess. So I would very much like it, in fact, I'm going to force you to actually write down which row operation you are doing, okay? Okay, so I'm going to write this in matrix form for sure. Okay, so this is it. 1, 2, minus 1, 3. 2, 5, minus 4, 5. 3, 4, 2, 12. Okay. Again, some people like to have a little dotted line here, or even then some people just put a full straight line there, just to keep in mind that this is an augmented matrix, but you can write it in or not, it makes no difference, okay? It's up to you. So I'm going to use Gaussian elimination, okay? So again, how does this work? We have 3 kinds of row operations that we can use. We can exchange any rows we want. We can multiply a row by a non-zero number, or we could add to one row a multiple of another row. Okay, so these are the 3 kinds of operations that we can use. And if we use them in the right order, we're going to get this matrix into upper triangular form, which means that we can now use back substitution to solve the system. Okay, so the point is always to get zeros below this diagonal here. So what you want is always basically to get zeros below this red line. Okay, so how do we do that? We have to use what we call pivots. The first non-zero number that you see, which in this case is here, we're going to use that to create zeros below it. Okay, so the first step you want is to make sure you have an entry which is non-zero up there. This is the case. We already have that for free. We're fine. Okay, so top left entry is not 0. We're happy. In fact, it's already 1, because if it's not 1, it's easier to, so you make it 1 by multiplying the row by the correct coefficient. Top left entry is actually 1, and we get that for free. Okay, and now we're going to make those 2 entries below it equal to 0. How are we going to do that? So let's move this. Okay, so I want to create, does it have to always be 1? At this point in your career, I'll answer yes, but theoretically, no. You can work with an entry which is not 1, but it's easier to work with a 1. Does that answer your question? Yes. Okay. I personally prefer working with a 1. So, okay. Take it from a pro. Okay, so what I'm going to do now, this is where I want you to, when you're going to solve this on the test, I want you to write this. So I'm going to do this. -2 times row 1 plus row 2. This is what I'm doing now, okay? Why? Because -2 times 1 plus 2 is 0. That's the whole point, okay? So if I'll just write -2 times row 1 here. I'll just write it here. So that's -2, -4, 2, and -6. And you have to be extra careful with those minus signs. If you go fast, I can tell you I've been doing these things for like almost 40 years. And I can tell you it's automatic. If you go too fast, you mess up. And if you mess up and you keep on going, you're digging a big hole and you're just going into the hole like that, and you'll have to do everything over again. So you might as well be careful at each step, okay? So -2 times row 1 is what you see here. I'm going to add row 2, 2, 5, -4, and 5. I'm going to add those. So I get 0, 1, -2, -1. Okay, so the resulting matrix that I get is this. So the only thing that is changed is row 2. So 1, 2, -1, 3. 0, 1, -2, -1. And this row hasn't changed. 3, 4, 2, 12. Okay. So this is the matrix, which is obtained by doing -2 times row 1 plus row 2. Okay. So we know these operations do not change the set of solutions. So this is good. Now I'm going to do the same procedure to get rid of that 3. So what do I need? I need to add -3. So that's -3 times row 1. I'm going to add that to row 3. This is the operation that I'm doing. Okay, so I'm just going to write this here. Once you start doing a lot of these, which is not the case right now because we're not doing very long on this, but if
Sir?
yep.
Sorry to interrupt, but the top left corner just needs to be other than 0, or it needs to be 1 as well?
Okay. It is possible to have it other than 1, but not 0. It can't be 0. If it's 0, then you can't do anything with it. Okay? It is possible to work with something which is not 1, but it is more complicated. So I'm telling you, use Gaussian elimination as defined. You make it 1. It's much easier.
Okay, thank you.
Okay. All right, so -3 times row 1 plus row 3. So I'll write here -3 times row 1. I'll write it here. So this is -3 -6, 3 -9. Row 3 is 3, 4, 2, 12. I'm going to add those. So I get 0, which is what I want, -2, 5, and 3. So now the resulting matrix is 1, 2, -1, 3, 0, 1, -2, -1, 0, -2, 5, 3. Okay, and notice that we have exactly what we want, which is in the first column, we get 1, 0, 0. That's what we want. Okay. Okay, so that's the first pass in the algorithm. Okay, so the next is we repeat exactly the same procedure, but now we handle the second column. Okay, so next pass, same procedure, for column 2.
Yep.
Yeah?
Sorry, wasn't for you.
Okay. All right, so I'm going to copy this. So now I've got this. Okay, so now what I want to do is to basically repeat the procedure without thinking about what's outside those two red lines. Okay, so now when I say top left, I mean inside the smaller matrix. Okay, so once again, we're lucky because this entry is not 0. And in fact, it is 1. So nothing to do. Okay. So that top left entry is already exactly what we want. So I don't need to do anything to it. I don't need to flip rows to get a non-zero entry there, because if it was 0, I'd have to exchange those 2 rows. If it was 5, I would multiply the whole row by 1/5. Okay. But so these we get for free. So finally, all I have to do now is get rid of the entry below it. Okay, so, oops, sorry about that. I want to keep that. Okay, so it's -2. I want to add 2 to that. So what I want to do is 2 times row 2 and add that to row 3. Okay, this is what I want to do. Okay, so let's just write down what those are. So 2 times row 2, this is 0, 2, -4, -2. Row 3 is 0, -2, 5, 3. I'm going to add those. I get 0, 0, 1, 1. So what we get is this. 1, 2, -1, 3, 0, 1, -2, -1, 0, 0, 1, 1. This is what I get. Okay. Now you see this is in the form we wanted. Okay. Now, of course, you don't have to write the corresponding system if you don't want to, but I'm going to do it here so that you can see what's going on. So the corresponding system is the following. So I'm going to write, so we know how to go from augmented matrix to system, system to augmented matrix. So this is x plus 2y minus z equals to 3. Then y minus 2z equals to -1, and z equals to 1. This is the system that corresponds to this new matrix. And again, we know that the operations we used do not change the set of solutions. So the solutions of this system are those that we're looking for, those of the original system. Okay, so this one is easy by back substitution. That's the whole point. Okay, so let's see. Do that here. Okay, so we just use back substitution. So z equals to 1, we get for free. It's right there. Okay, then I substitute that in the previous equation. Y minus 2 times 1 equals to -1. So that's going to give me y equals -1 plus 2, which is 1. So y equals to 1. Okay, and then finally I go to the top equation, which is x plus 2 times y, which is 1. minus z, which is 1, equals to 3. So x is equal to 2. So we have a unique solution, which is x equals to 2, y equals to 1, z equals to 1. What should I do at this point? If I'm a good student and I'm smart and I have time, I take those values and I put them back into the original system. Okay, let's do that. Okay, so 211, I'm just going to go back up, copy that. So I found 2, 1, 1. Let's check. 2 plus 2 minus 1. This is 3. Now, if you stop there, that's bad because you see that that one, we found the value of x using y and z using that precise equation. So it's later that it might mess up. Let's try this. 2 times 2 plus 5 times 1 minus 4 times 1. This is 5. Yes, we're happy. Then 3 times 2 plus 4 times 1 plus 2 times 1. This is 12, and so we're happy. We know it's good. That's it. Okay. And if it doesn't work, then you know you have to do it again. So it's easy to check, right? So if you have time to do it, it pays off to do it, right? All right. Question. Yep.
In WebWork, it says R2, meaning row 2, equals -1 times row 1 plus
Yeah.
R2. So that
Yeah.
means that's the result of row 2, isn't it?
Say that again. Sorry. Just it's good.
So basically, it tells me to perform the calculations as follows. And one of them is, it says R2 equals -1 times R1 plus R2.
Yeah. So yeah, you replace row 2 by
The result,
yes. Yeah.
the result of that.
That's another way. Yeah.
Okay, I've done it, but I have like a mistake. Okay.
Yeah. Okay. 28. Should I do another one?
I'd go for it. But
All
just before that, I have a question. Sorry, I have
Yep.
many questions.
All right.
Okay. In the augmented matrix,
Yes.
when you have a matrix, it's -2, -5, and 0 on one row. So it basically means it means -2x minus 5y equals 0, isn't it?
Is the row -250 or -2 minus 50?
No, -2 minus 5,
Okay.
0.
Yeah. So it means -2x minus 5y equals to 0.
Equals 0. Yeah, that's what I did. The equivalent linear system. But I don't understand when he says use x1 and x2 to enter the variables x1.
You see, you can use whatever names you want for variables, right?
Okay, yeah.
So they're asking you to do it. So using like that.
Oh, okay. I see. Okay, thank you very much.
Yeah, because when you have an augmented matrix, you don't have the names of the variables. You can choose whatever you want. But
Oh, yeah. Okay.
for the machine to recognize your answer, it's telling you to use those names of variables.
Okay, thank you, sir.
Yeah. Okay, let's do 28, 28, 28. Okay, x plus y plus 2z. Isn't that the same? That looks almost like the one I just did. No, it's not the same, but okay. Okay, x plus y plus 2z equals to 3. You know what? I'm going to change it. 2x plus y plus 2z equals 2. No, sorry. I'm going to change this. It's the same question, basically, but 2x plus 3y plus 5z equals to 7. X plus y plus 2z equals to 3. And 3x plus 5y plus 7z equals to 12. Okay, so the actual question is A, write as a matrix equation, B, find the augmented matrix of the system, C, solve it. But I just want to solve it, okay, using Gaussian elimination. Okay, so what I'm going to do first is write it in matrix form. Augmented matrix is 2, 3, 5, 7, 1, 1, 2, 3, 3, 5, 7, 12. So this is the augmented matrix of this system, okay? So the algorithm we've seen, what it says is, okay, look at the top left entry. Is it 0 or not? If it is 0, you have to exchange rows. Now, I look at it now and it's a 2. Okay, so if I just follow blindly the algorithm that I gave you, it's going to be, I would divide this row by 2. I would multiply by 1/2, but I'm going to introduce fractions if I do that. Okay, so let me write this. So following, it's fine, but there's a smarter way of doing it. So following the algorithm, we should multiply row 1 by 1/2, but we're going to get fractions. Okay, so what would be a smarter way to do this? I want to get a 1 in that top left corner. Rather than multiply the row by 1/2, there's another way of doing it. You can use any basic row operation that you want. Any suggestions?
I'm sorry, what's the question, sir?
So I want the top left entry to be 1. Okay, the algorithm says one way to do it, which of course will work, is to multiply that row by 1/2. But I'm going to introduce fractions in there, which I would rather avoid at this point, okay? Because they're going to start going all over the place. But there's another way of making the entry there 1 without introducing fractions.
Change row 1 to row 2?
Yes, so if you exchange those 2 rows, then you'll get what you want, exactly, okay? So I'm going to do that. So I'm just going to copy this here. Okay, so we can instead exchange rows 1 and 2, right? This is totally legit. I'm allowed to do any elementary row operations that I want. So that's what I'm going to do. 1, 1, 2, 3, 2, 3, 5, 7, 3, 5, 7, 12. So I can do that. So I've got my top left. So top left entry is 1. So I'm happy. Okay. And now I'm going to do, so here for this example, I'm going to do it how I would do this. Okay. So I went a little slower in the previous example. Okay. But I'm going to do both these, the next operations. Yes, correct. I'm going to do both these, the next two operations in this with the same matrix. I'm not going to write a whole bunch of matrices. So now I'm going to do -2 row 1. I'm going to add that to row 2, right? Because I want to make that entry 0. And -3 row 1. I'm going to add that to row 3. So this will give, so the first row doesn't change. 1, 1, 2, 3. So -2 plus 2 is 0. -2 plus 3 is 1. -4 plus 5 is 1. -6 plus 7 is 1. -3 plus 3 is 0. -3 plus 5 is 2. -6 plus 7 is 1. And -9 plus 12 is 3. Okay. I went a little fast there, but semi-fast, so it should be okay. But again, be very careful. It's like you make one arithmetic, so there's a lot of numbers, right? But if you mess up one number, the whole thing just messes up completely. So that's why you have to be careful. Okay. So this is my resulting matrix, and hopefully I didn't mess up, but I'll see later for sure. But I think I'm good. So I'm going to go to the second pass of the algorithm. My looks weird. No, okay. So now I'm going to repeat the procedure with the second column, right? Again, if I look at the pivot, the entry that I'm interested in, it's this, it's all good. So it's already 1. We're happy. Okay, so these examples are a bit simpler, in fact, than a more general example would be. Okay, so all I need to do now is -2 row 2 and add that to row 3. Okay. Now, I want you to pay attention to something, because you see how crucial it is that those two first entries are 0, because when you start messing around with row 2, row 3, nothing's going to happen in those with those zeros, right? Nothing bad can happen. Whatever you do is always going to stay 0, right? But if they were not 0, then things would start to happen. You have to be careful in which order you do things. Okay, so here's what we get. This is 1, 1, 2, 3, 0, 1, 1, 1. So I do -2 plus 2 is 0, -2 plus 1 is -1, -2 plus 3 is 1. So this is what I get. Okay. So this is the matrix of the following system. X plus y plus 2z equals to 3. Y plus z equals to 1. Minus z equals to 1. And again, these are easy to solve. We do back substitution. So z equals to -1. Then go up, y minus 1 equals to 1. So y equals to 2. And x plus y, which is 2, plus 2z, which is minus 2, equals to 3. So x equals to 3. Okay, I've got 3, 2, minus 1 as my solution. So I'm going to go and check. Okay, so I'm going to go to this system here and check it. So what did I say? We got 3, 2, minus 1. I hope. Okay, 3, 2, minus 1. Let's check. So that's 6 plus 6 minus 5. This is 7. Okay, but the first equation is always, I mean, unless you did something really, really bad, it's always going to work by the method we use. It's the next two, which are, so 3 plus 2 minus 2. This is 3. Yeah. 9 plus 10 minus 7. That's 12. Yes, we got it. Okay, so that's it. I know it's good. All right. Somebody wanted some exercises from chapter 9, such as, give me a problem from chapter 9.
Sir, I just missed a part.
Yep.
Sorry. What's the, where did you get the 6 plus 6 minus 5?
I'm substituting these in here.
Oh, okay, okay. Okay. I see.
Yeah.
Thank you.
Okay. Chapter 9. Give me. Shoot.
Yeah, sigma. He says sigma.
Okay. Yeah, okay, let me just go here. Okay, let me do a couple from the WebWorks because these were like, I don't know if it's, no, actually, no, let's not. Let's go, here. Okay. That's not what I want either. Sorry, I'm getting there. Okay. So this is from the, I know you can't see my iPad. Just let me write it up while I see this. This is from the problems list. So you're asked to evaluate sum I equals 1 to 5, 2i squared minus 3.
We can't see this one either.
I know. That's what I said. I said I need to write it down before
Oh, sorry.
Yeah. Okay, and the other one I can do is, okay, I'm gonna do this one. This one I'm making up. J equals 0 to 3 of 1 over 5. Okay. The first one. So this one is from the problems list. Okay. The second one is there was one like that in the WebWorks, which was one of the two trickiest problems there. Okay. So the first one, again, what does the sigma notation mean? It says you have a generic term in which you're going to input the values of the index between the value you see at the bottom and the value you see at the top. So here in the first example, I goes from 1 to 5, so it means 1, 2, 3, 4, 5. You will substitute into that in what you're supposed to add, the summand, and you add all of these up. So 2 times 1 squared minus 3 plus 2 times 2 squared minus 3 plus 2 times 3 squared minus 3 plus 2 times 4 squared minus 3 plus 2 times 5 squared minus 3. A different question. Okay, so you can add those up, but you see the principle, right? Index goes from bottom value, top value, increases by 1. You replace the value in that summand to I squared minus 3. So I will go from 1 to 5, 1, 2, 3, 4, 5. You get 5 values, you add them up. That's what it means, okay? So in this case, we'd get minus 1 plus 5 plus 15 plus 29. These look weird. 47, which is some number, which I don't really care about. Okay, so some number. Okay, so that's it.
Isn't it 1 instead of minus 1?
Nope. 1 squared is 1. 1 times 2 is 2. Minus 3 is minus 1.
Okay, my bad.
Yep. Yeah, because you're thinking 2 times 2 minus 3. That's what it looks like, but it's 1 squared, which is 1 times 2. Okay. Okay, so the other one is one of the trickier ones, okay, which is this, okay? Your summand here is 1/5, okay? So we have to think like machines. We have to be really stupid here, right? Just you want to be like a machine. Machines are not smart. They're stupid. They just do what they're told, okay? So what you're supposed to do is take that expression, evaluate it at all the values of the index j from 0 to 3. You get a result and you add all of these things up, okay? So what is that expression when j equals to 0? It is 1/5, right? So that's when j equals to 0. What is the value of 1/5 when j equals to 0? It is 1/5. Okay. What is the value of 1/5 when j equals to 1? It is 1/5. What is the value of 1/5 when j equals to 2? It is 1/5. Yes? And what's the value of 1/5? I know it sounds terrible, but what's the value of 1/5 when j equals to 3? It is 1/5. So that's what happens, okay? So it's a constant, so its value does not change for different values of j. It is always the same value. So that's the value of the summand for all these values of j. So this is 1/5 plus 1/5 plus 1/5 plus 1/5, and this is 4/5. Okay, it's a constant summand. Okay, so because 1 over 5 is equal to 1 over 5 for any value of j, right? It doesn't change. There's no j, so it never changes. Okay, so there was a one like that in the WebWorks, which is one of the trickier ones. Okay, does that make sense? Hopefully it does.
Yeah, it makes sense, sir. Sorry.
Yay. All right. Okay. Something else you want me to do? Can we do the reverse one? The one you have to find. Yeah, these are the hardest ones. That's really by far the hardest one is the reverse ones. Yes. So here's an example. Find an expression sum, let's say j equals something to something of something for, okay, let's start with an easier one. 4 plus 8 plus nope. Let's make it even easier than that. Okay. I'm going to do one, okay, but I'm going to tell you right now. So how many of you are here? Too bad for the others. And there's only 14 of you. I'm not gonna ask you one like that in the test. Okay, I can tell you right now. I'll do this. I'll do a couple, but I'm not gonna go there because it's like it's super interesting, but it's just totally taking us somewhere else. Okay, it would take a lot of practice to do these, and not on the test. No, I'm not gonna do one like that on the test. Okay, so I'm just going to do this easy one here. So the one on the WebWorks was really tough, but it was there to challenge you, to make you think, to make you
Yeah,
see.
there was one with -1 plus
Yeah.
2 -4 plus 8 minus 16.
Yeah, that was the toughest one. That's a tough one. There's a lot of little things involved in doing that. You have to think about it. You have to know other stuff. So it's the thing is that you have a lot of freedom here. Okay, so I want to find an expression. It's the summand which is the key, right? So I want to find a summand, an expression such that when I input values of an index one after another, I'm going to generate 4, 6, 8, 10, 12. Okay, but so basically what you have to do is sort of see the pattern, and this can be sometimes very difficult. So the first thing you have to see the pattern, but here the pattern is not too bad, right? You see that this is 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5 plus 2 times 6. Okay, so you have to spot if there's something that's increasing by 1 each time. Yes, there is. If you look at this, right? So what you're looking at is a single expression in which you change the value by 1 each time. Okay, so here's how you could do this. This is the sum j equals from, well, 2 to 6, there for free, 2 times j. Right, that's one way of doing it, but there are many other ways I could write this. If I force you to start at j equals to 1, you'll have to write something slightly different. Not too bad, but okay.
So basically the one we'll have on the exam will be the one with the index?
I mean, it's not going to be a reverse one. That's
Okay,
what I'm
okay,
telling you. Okay, not like that.
okay.
I'm not going to go there. And I prefer telling you because I don't want you to waste your time trying that. I mean, it's not a waste of time in the universal sense, but it's a waste of time in terms of what you need to do for this course. Okay, especially in the middle of a flu pandemic. So, okay, all right. Something else. Dessert, coffee.
I think it's pretty good for me.
All right, good. Just the bill.
How long we'll have for the exam on Thursday?
Depends who you are.
Oh, okay, okay. So a regular
When it's
guy.
yes, the when a regular guy gets an hour.
Okay.
Yes, just like it's the same thing as the previous test. Same thing.
Plus 15 minutes to
Yeah,
publish it?
yeah. Yes,
Okay.
that's right. And this time you're gonna lose marks if you don't make it in time because last time a third of the class got in late.
Oh boy.
But you
Okay.
did so badly so I didn't remove anything. So, but this time it'll be written on the test. If you're late, you lose marks. That's it. Yeah. Okay. Let me
Sir, do you think at some point we'll come back to campus? I mean, I heard that
never
perhaps
ever
half,
again. I
I mean,
when
I heard that half the next semester will be, I mean, it all depends on the situation, obviously, but
I think
I
that's will be
perhaps half would be
no,
online and the
I
other
can
half will be on
I'm
campus.
I'm willing to bet a lot of money that you're not gonna set foot in the college officially
yeah, I
next
think the same.
semester. It's gonna be online, the whole thing. I mean, the only thing that's gonna change is the vaccine. Is when enough people are vaccinated, then things will start to change. And
But
that's not
sir,
gonna happen for a while.
yeah, do you think that they're gonna say, well, the college will say, well, you're gonna have to get the vaccine if you wanna attend classes on campus?
That's I don't
I
know.
don't suspect they would, because what happens if you can't get the vaccine for some reason?
Yeah, and they
I
can't like force you to do that. The government can't. So
And
I
not just that, but what if you're unable to get to the place where the vaccine's being injected?
yeah, I have no idea what's going to happen. I mean, I'm not I
But
don't have enough
sir, what do
facts.
you think about nanotechnology in vaccines? I mean, I've read.
Oh god, don't.
I, I mean,
No.
it's not. I didn't read that from
No way.
straight an eerie website or something. It was like on
Okay,
the Guardian.
I'm gonna tell you something. Okay, so you're don't. I'm a scientist, okay, and I
Okay.
know a lot of scientists, and these are just like all scientists that I know are just like smart, nice people. Okay, that's what you should. That's what you should always think about. Scientists are smart, nice people for the vast majority of them. Okay, so all these conspiracy theories is just total crap. I
Oh
mean,
yeah,
and it's
yeah.
just like
I'm with
no,
you,
no,
sir. I'm not
no.
saying something. I'm just saying that it's a new way of making vaccine, and I was just curious.
Oh, in
What
that
is it
sense, I
exactly?
thought you were talking about
No,
their.
no, no. I'm not saying
Okay,
anything
all right, okay, no,
conspiratory
no.
or anything. I'm just saying they're developing a new brand of, not a brand, but it's a new way of making vaccines by using nanotechnology. And I was wondering,
I
how would that be converted into?
I have absolutely zero knowledge of these things. As far as I know, there might be new ways of making these vaccines, but I haven't heard about anything to do with nanotechnology. As what I know, what I've heard about nanotechnology is that there's not much happening there, I can tell you. That's what I know. Okay, so and so, but maybe I'm wrong. But these vaccine are just they're vaccines. They're just it's the usual stuff. We've known how to make them for a long time. Maybe they're making them differently in terms of producing them, but it's the same you're just getting a nice version of the virus, right? It's a version of the virus that doesn't hurt you, so your immune
Well,
system
well, it's
responds to
technically
it.
not a version of the virus, right? It just tricks the immune system
Mhm,
into
mhm.
thinking that it's the virus, right?
Yes, exactly. Yeah.
I thought it was a
So,
version of the virus that was weakened or dead, but still a version of it. And that's why some vaccines give you much milder cases of the virus they're supposed to cure.
yeah. So, but we've known how to make these. We, as in human beings, have known how to make these for a long time, and we know they work, and they're very good. And so, of course, now it's different because
Yeah,
they've
it's
been
way
done so
different.
fast, right? It was done really, really quickly. So, who knows? But I'm as far as when they'll be approved and when they'll be distributed and who's gonna get them first, and who
I think
knows?
it'll be frontline workers that will get it
Yeah,
get
sure,
them
of
first,
course.
and elders
But
as well.
so how long will it take for it to get to you guys? You know?
Yeah,
That's a
that
good
will be long,
question.
I think.
Yeah. So
The
I don't
winter
know.
semester will end before
Oh
that.
yeah, I think so. I think so. Yes.
Yeah, for sure.
Yeah. But maybe next year, who knows? I mean,
Yeah, we
that
will
would
probably
that's
finally visit the campus.
yeah, that's right. You guys have never been there.
We have no idea what it is.
I mean, the only thing I've known about the campus is when I go online on the Champlain website, there's in
Yeah,
virtual
some
tour,
picture.
Oh yeah,
and then you
wow.
see a boring class of computer science with just tables, and then you see laptops all around. Is that it? I mean, I've seen just one classroom. Or all classrooms look alike?
Yeah, most of them look, well, not all of them, but yes. There's a whole block where all the classrooms are basically very, very similar. But then there are labs which are very different. So ah, it'll be a surprise. It'll be nice. You'll see that next year.
I
Yes.
hope.
Yeah.
Hopefully, yeah.
Yeah.
Do you
Okay.
teach also stuff of the for second semester, third semester? I mean,
No. I teach
okay,
in usually what I teach in the second semester is Calculus 3 and discrete math for students in the computer
math and computer
science.
science.
Yeah, that's
Okay,
right. Yeah, that's
okay,
what I.
but the other teachers in computer science, do they also teach in other year students, or just like I'm wondering if I will have the same teachers next
I
semester?
think
And
one or two of our
It's
teacher teach for
possibly
the
but I
semester.
don't know. I don't know many of the. I mean, I think I know like a couple of people in the computer science department, but I don't know them very well. So yeah,
oh, okay.
yeah, yeah. You can tell me about them sometime. Okay. All right.
Thank you very very much, sir. Appreciate
Yeah,
Okay.
thank you.
See
it.
you.
Bye.
Cheers.
See you next time.
Oh, I think it.
Bye.
Have a good day, sir.
Bye.